Hello, welcome back. So today we are going to take the topic vibrational spectroscopy, which is also known as infrared spectroscopy. So let's go to our video. Vibrational spectroscopy. So vibrational spectroscopy will always give spectrum in the IR region or infrared region. Therefore we call it as infrared spectroscopy. Okay. So vibrational spectroscopy is otherwise known as infrared spectroscopy or IR spectroscopy. Why? Because we will be always getting spectrum in IR region. Okay, so depending on the region in which we are getting spectrum, we are classifying spectroscopy into IR, UV, microwave, etc. Okay, so vibrational spectroscopy is otherwise known as infrared spectroscopy. Now, what is the principle of infrared spectroscopy? The principle of infrared spectroscopy is there should be change in dipole moment. Okay, there should be change in dipole moment. That is the principle of IR spectroscopy. So only the molecules which exhibit change in dipole moment will give spectrum in IR spectroscopy, or we can say that those molecules will be IR active. Okay, so which molecules are IR active? Only those molecules which have a change in dipole moment during vibration. Okay, so change in dipole moment during vibration is the essential condition for exhibiting IR spectra. Alright, so all those molecules which have a change in their dipole moment during vibration, they are called IR active. Okay, they are called IR active. Now, what is this change in dipole moment? Dipole moment means it's like a tug of war game. That's it. Say for example, if I represent a molecule HCl, okay, HCl, hydrogen is delta positive and chlorine is delta negative. Now, if you consider hydrogen and chlorine, chlorine is more electronegative than hydrogen. Okay, so chlorine is more electronegative than hydrogen. What is electronegativity? Electronegativity means pulling the electron pair towards itself. In case of HCl, hydrogen have an electron and chlorine also have an electron, and those electrons should be delocalized in this bond. Okay, but since chlorine is more electronegative than hydrogen, chlorine have a tendency to pull both the electron towards itself. Okay, since both the electrons lie towards chlorine, it will have a partial delta negative charge. Delta represent partial, not complete. It's only partial delta negative charge, and hydrogen will have a partial delta positive charge. Okay, we know that electron is always negative in charge, right? Electrons are negative in charge and protons are positive in charge. So the molecule that loses electron will have a positive charge, and the molecule which gain electron will have a negative charge. Okay, so in the case of HCl, hydrogen will have a positive charge and chlorine will have a negative charge, but that will be only partial. Okay, to represent partial we have to represent delta. All right, so this is dipole moment. Dipole moment means there should be a charge separation. All right, so only those molecules which have this charge separation, okay, they can represent IR spectroscopy. All right, so in the case of HCl, that is again IR active, right? And if I write the molecule CO, CO is C triple bond O. Oxygen is more electronegative than carbon, so oxygen will have a partial delta negative charge and carbon will have a partial delta positive charge. It is also IR active. But if I write the molecule H2, is it IR active? H2 means H single bond H, right? Both are same molecules, both are same atoms. Since both are same atoms, there won't be any charge separation. In the tug of war game, if you have equally like fat person on both sides, nothing will happen, right? They can't move the rope to either of the sides. So same case, here both are hydrogens. They cannot pull electrons from one hydrogen to another, right? So the electrons will be delocalized at the center position only. So these type of molecules, that is homodiatomic molecules like H2, N2, then what? O2. These type of molecules are IR inactive. They cannot give IR spectra. Why? Because both are same atoms, right? So there won't be any charge separation and there won't be any change in dipole moment. So in the exam it will be asked why homodiatomic molecules are IR inactive. So why they are IR inactive? First reason should be there is no dipole moment. There is no net dipole moment since both are same atoms. So since the absence of change in dipole moment during vibration, we can say that these molecules are IR inactive. Alright. So that is the basic principle of IR spectroscopy. So any molecule can give IR spectra if there is a change in dipole moment. Alright. Now consider the case of a diatomic molecule. Say for example HCl. I said HCl is IR active, right? So one atom is hydrogen. In the other end you will have chlorine. So hydrogen and chlorine. Hydrogen will have a partial delta positive charge and chlorine will have a partial delta negative charge. So generally we will be considering these molecules which exhibit vibrational spectroscopy as a simple harmonic oscillator. Okay, so generally we call them as simple harmonic oscillator, SHO. So for a simple harmonic oscillator we have to learn two equations. Okay, two equations need to be learned. First equation is vibrational frequency nu. Vibrational frequency nu, because what is frequency? Frequency is number of oscillations per second or number of vibrations per second in this case. Okay, so number of vibrations per second is its vibrational frequency. So what is vibrational frequency? Vibrational frequency is represented using the letter nu. Nu, we usually write it like a V. Okay, nu. So for a simple harmonic oscillator, the vibrational frequency nu will be equal to, nu is equal to 1 by 2 pi into 1 by 2 pi into root of k by mu. That is the equation for a simple harmonic oscillator. Okay. So for a simple harmonic oscillator, the vibrational frequency nu is equal to 1 by 2 pi into root of k by mu. Now, what is k? What is mu? K is a force constant. Okay, what is K? K is a force constant and mu is the reduced mass. Okay, K is the force constant and mu is the reduced mass. Now, mu is given by an equation. Mu is equal to m1 m2 by m1 plus m2. This is the equation for finding mu. Okay, mu is the reduced mass and reduced mass is calculated using the equation m1 m2 by m1 plus m2, where m1 is the mass of first atom, m2 is the mass of second atom. Initially we have drawn a picture, right? So m1 is the mass of first atom and m2 is the mass of second atom. So mu is equal to m1 m2 divided by m1 plus m2. So that is the equation for calculating reduced mass mu. Now, so till now what we have learned? We have learned that vibrational spectroscopy is otherwise known as infrared spectroscopy. So vibrational spectroscopy is otherwise known as infrared spectroscopy. Now, infrared spectroscopy, what is the principle of infrared spectroscopy? All the molecules can exhibit a change in dipole moment during their vibration. Homodiatomic molecules will be always IR inactive because there is no change in dipole moment. Alright. Next we have to learn about the vibrational frequency. So for calculating vibrational frequency, we will be considering the molecules as a simple harmonic oscillator. So all the molecules which can give IR spectra can be called as a simple harmonic oscillator. For a simple harmonic oscillator, we need to calculate the vibrational frequency. Vibrational frequency is represented using the symbol mu. So mu is equal to 1 by 2 pi into root of k by mu, where k is the force constant and mu is the reduced mass. Force constant in the sense, if you consider a molecule CO, that is the strength of the bond. Okay, strength of the bond can be calculated using the force constant. Alright. Now mu is equal to m1 m2 divided by m1 plus m2, where m1 and m2 are the masses of first molecule and first atom and second atom respectively. Alright. Now, so next we have to learn about the energy of vibration. What is E vibration? E vibration is equal to V plus half into H nu 0. Okay, so E vibration is equal to V plus half into h nu 0. Problems will be asked from this section for calculating the energy. They will be providing you the frequency and will be asked to find energy. Alright. So E vibration is equal to V plus half into h nu 0. Now, what is nu? Nu is frequency. We have already learned vibrational frequency is represented as nu 0. Alright. Now, what is V? V is our vibrational quantum number. What is V? V is vibrational quantum number. So, we can have values 0, 1, 2, 3, etc. Alright. So, we can have value 0, 1, 2, 3, etc. What is V? V is vibrational quantum number. So, E vibration is equal to V plus half into h nu 0. Now, since it is energy, it should always be represented in joules. Okay, so always represented in joules. Now, when the value of V is 0, when V is 0, we will get E0. E0 is equal to 0 plus half into h nu. 0 plus half into h nu will be half h nu. Right? Okay. Now, when V is equal to 0, E0 is equal to half into h nu 0. Now, when V is equal to 1, you will have E1 is equal to 1 plus half. 1 plus half will be 3 by 2. So, 3 by 2 h nu. Right? When V is equal to 2, you will have E2. E2 will be equal to 2 plus 1 by 2 will be 5 by 2. So, 5 by 2 h nu. Alright, so accordingly you will get different values for E if you substitute different values for V. Okay, so we can have values 0, 1, 2, 3, etc. up to n, and depending on that you will have different energy values also. We are going to draw a curve for simple harmonic oscillator depending upon the values of E. So this is a diagram, or this is our curve for the simple harmonic oscillator. So that is a plot of energy versus internuclear distance R. What is internuclear distance? So if you consider the molecule HCl, so from the center of hydrogen to center of chlorine, the distance between the center of hydrogen to the center of chlorine, that is called internuclear distance. Okay, the distance between the nucleus of two atoms in a molecule. So we'll be plotting a diagram with energy versus internuclear distance R, and you will have a U-shaped curve. Okay, and U-shaped curve will be there. In that you will have different lines with equal spacing. What is the spacing between these two lines? That will be always h nu. Okay, in every case you will have h nu. How you will get h nu? If you subtract 3 by 2 h nu minus 1 by 2 h nu. 3 by 2 h2 minus 1 by 2 h nu will be h nu. 5 by 2 h nu minus 3 by 2 h nu will be h nu. So if you subtract the values of the higher level and lower level, you will get the difference h nu there, and that is the spacing between all the levels. Okay. So if you draw up to V is equal to 80 or V is equal to 90 also, your spacing between the two levels as h nu. Fine. This is for a simple harmonic oscillator. Now, V is equal to 0 is the lowest value that energy can have, right? So if you substitute the value V is equal to 0, you will have energy 1 by 2 h nu. So energy cannot go beyond 1 by 2 h nu, right? So that is the lowest value energy can have, and that is called our 0 point energy. Usually repeatedly asked in exam, what is 0 point energy for a simple harmonic oscillator in the case of vibrational spectroscopy. So what is 0 point energy? It is the lowest energy which an energy level can occupy, or lowest energy which is obtained when V is equal to 0. When V is equal to 0, E is equal to half h nu, and that is the lowest energy that can have, and which is called the 0 point energy. Alright, so what is 0 point energy? The energy when we have V is equal to 0, or what is the value for that? That is half h nu. Alright, so that is 0 point energy. So this much things we have to learn about a simple harmonic oscillator. What is the vibrational frequency? What is the energy equation? How we can calculate different energy values, and we have to plot the diagram of energy versus internuclear distance. That is done. Okay. Next we have to learn about unharmonic oscillator. Okay, so simple harmonic oscillator is only exists in theories. Generally, when we speak about the molecules, they are not simple harmonic oscillator. There is some kind of unharmonicity. So next we have to learn about the unharmonic oscillator. So for an unharmonic oscillator, there will be an unharmonicity constant. An unharmonicity constant is always represented as chi e. Okay, so this is called as chi. So chi e is the unharmonicity constant, and that will also add on to our energy equation. So for an unharmonic oscillator, the energy of vibration is given as E is equal to V plus half into H nu 0, same as our simple harmonic oscillator, minus V plus half the whole square into H nu into chi e. Okay, so once again, E vibration is equal to V plus half into H nu minus V plus half the whole square into H nu into chi e. Okay, that is the equation for our unharmonic oscillator. Okay, this is our energy equation. Now in this case also we have to plot a diagram with energy versus internuclear distance. This is a diagram for an unharmonic oscillator. For an unharmonic oscillator, we'll be plotting the diagram with energy versus internuclear distance, and you will have a slightly open V curve. You will have a slightly open V curve. Okay, so the spacing keep on decreasing as you go from lower to higher level. That is a speciality of unharmonic oscillator. Okay, in the case of simple harmonic oscillator, we have equal spacing between all the levels, but in this case you will have unequal spacing between all the levels, and the spacing keep on decreasing as you go from lower to higher level. Okay, so for V is equal to 0, you will have a corresponding energy value. V is equal to 1, you will have a corresponding energy value. 2, you will have a corresponding energy value, etc. Now we have to show the transitions. Okay, transitions from V is equal to 0 to V is equal to 1. Okay, so transition from V is equal to 0 to V is equal to 1 is called fundamental frequency. That is called fundamental frequency. Very important. Okay, that is called fundamental frequency. So transition from V is equal to 0 to V is equal to 1 is called fundamental frequency. Now transition from V is equal to 0 to V is equal to 2. Transition from V is equal to 0 to V is equal to 2. That is called our first overtone. That is called first overtone. Fine. Now next transition, that is from V is equal to 0 to V is equal to 3. From 0 to 3 we call it as, from 0 to V is equal to 3 you call it as second overtone. Okay, so after that overtones will be less visible, so we don't have to learn all that. Only you need to learn these 3 transitions. So transition from V is equal to 0 to V is equal to 1, that is called fundamental transition. Transition from V is equal to 0 to V is equal to 2 is called first overtone. Transition from V is equal to 0 to V is equal to 3, that is called second overtone. Okay, so in this, fundamental frequency will be highly intense than the other two. Okay, that will be clearly visible for us. The other two will be slightly less visible, and above that, after second overtones will be there, but that will be of very less intensity, and that will not be visible at all. Alright, so when you are learning unharmonic oscillator, we need to learn about the E vibration equation. In that you need to specify the chi E, that is unharmonicity constant. After that we have to plot the diagram with energy versus internuclear distance. We have to specify about the spacing between the levels. The spacing keep on decreasing as we move from lower to higher energy levels. Next, we have to show the transitions from V is equal to 0 to V is equal to 1, V is equal to 0 to V is equal to 2, V is equal to 0 to V is equal to 3. Whenever we are learning a spectroscopic technique, we have to learn selection rule. Okay, what is the selection rule for that? Now, in the case of a simple harmonic oscillator, the selection rule is delta V is equal to plus or minus 1. Delta V is equal to plus or minus 1 is the selection rule for a simple harmonic oscillator. Okay, And for an unharmonic oscillator, you will have the selection rule. Delta V is equal to plus or minus 1, plus or minus 2, plus or minus 3, etc. Okay. So selection rule for an unharmonic oscillator is delta V is equal to plus or minus 1, plus or minus 2, plus or minus 3, etc. It can go up to n. Okay. What is selection rule? Selection rule says that, see, here delta V is equal to plus or minus 1. That means transition can happen from V is equal to 0 to 1 and from 1 to 0. So always the molecules can get excited from one level to another level, right? So plus or minus 1 in the sense it can go one level just above that or one level just below that. Okay, that is plus or minus 1. Now plus or minus 2 means from V is equal to 0 to V is equal to 2. It can jump 2 levels higher and 2 levels lower. V is equal to plus or minus 3 means the molecules can jump 3 levels higher and 3 levels low downside. Okay, so that is meant by plus or minus 1, plus or minus 2, plus or minus 3. So in the case of a simple harmonic oscillator, it can have only the transitions plus or minus 1. That is, molecules can jump either one level higher or one level lower, not beyond that. Okay. But in the case of unharmonic oscillator, as you can see from the diagram, it can jump 1 level, 2 levels, 3 level or 4 level depending upon the intensity of the energy provided. Okay. So the selection rule for anharmonic oscillator is delta V is equal to plus or minus 1, plus or minus 2, plus or minus 3, etc. So vibration. So how to calculate modes of vibration? We have two types of equations. First one is for linear molecules, the number of modes of vibration is equal to 3n minus 5. Okay, so for linear molecules, number of modes of vibration is equal to 3n minus 5, where n is the number of atoms present in that molecule. Okay, where n is the number of atoms present in that molecule. Now, let's see an example. If you consider the molecule CO2, CO2 is a linear molecule, right? CO2 is a linear molecule. Now, how to calculate the number of modes of vibration for CO2? That is equal to 3n minus 5. So 3 into n. N is number of atoms. How many atoms are there? 1, 2, 3. 3 atoms are there. So 3n minus 5. 3 into 3 is 9. 9 minus 5 is 4. So it will have 4 modes of vibration. Okay. So for linear molecules, how to calculate number of modes of vibration? That is equal to 3n minus 5. So where n is the number of atoms present in the molecule. So in the case of CO2, number of modes of vibration is 4. So there are two types of vibrations. First is stretching and second one is bending. So either it can stretch or it can bend. So how to calculate how many stretching vibrations are there and how many bending vibrations are there? For that also we have one equation. How many stretching modes are there and how many bending modes are there? Stretching modes is always calculated as n minus 1. n minus 1 stretching vibrations will be there, and bending modes are always calculated as bending is equal to 2n minus 4. Okay, so these are the equations for calculating how many stretching modes are there and how many bending modes are there. Now let's calculate stretching mode. Stretching mode is n minus 1. So in the case of CO2, how many mole atoms are there? 3 atoms. So n will be 3. So 3 minus 1, 2. So number of stretching vibrations are 2. If you know the total vibration is 4, and in that stretching vibration is 2, then automatically you can calculate bending, right? Bending means 4 minus 2. So 2 modes will be bending. In the case of CO2, there is 2 stretching mode and 2 bending modes. Alright, now let's substitute in the equation and see. Bending modes is equal to 2n minus 4. That is 2 into 3 atoms are there. So 2 into 3 minus 4. 2 into 3 is 6. 6 minus 4 is 2. Again we got the answer. So you can go through either method. Either you can calculate using this stretching and bending modes. Otherwise you can calculate the total modes of vibration and stretching modes, and from that you can subtract both the values for getting bending modes. Alright, So every IR active molecule will have a stretching frequency and a bending frequency, or you can say that they'll have stretching modes of vibration and bending modes of vibration. So how to calculate stretching and bending modes? So number of vibrations can be calculated using the equation 3n minus 5 for linear molecule. Okay, for non-linear molecule it will be different. For a linear molecule, number of modes of vibrations will be 3n minus 5, where n is the number of atoms present in the molecule. Okay, so from that you will get the value. Now for calculating separately the stretching and bending modes, we have two more equations, that is n minus stretching modes will be there and 2n minus 4 bending modes will be there. Alright, so this is the case of carbon dioxide, that is a linear molecule. Now let's consider a non-linear molecule. For a non-linear molecule, say for example water. Water is a non-linear molecule. It have a shape like this. Okay, it have a bend structure, and water molecule is an example for a non-linear molecule. In the case of non-linear molecule, number of modes of vibration will be equal to 3n minus 6. Okay, 3n minus 6 is the number of modes of vibration for a non-linear molecule. Okay, so for a linear molecule it was 3n minus 5. Okay, don't get confused. For a linear molecule it was 3n minus 5, and for a non-linear molecule it was 3n minus 6. Now here we considered the example of carbon dioxide. Okay, so for a linear molecule we can take the example of carbon dioxide, and for a non-linear molecule we will be considering the example of water. Now let's calculate the number of modes of vibration for water. Modes of vibration. How many modes of vibrations we have? So 3 into n will be number of atoms in the molecule. How many atoms are there? 3 atoms are there, right? So 3 into 3 minus 6. 3 into 3 will be 9. 9 minus 6 is 3. So you have 3 modes of vibration in the case of water. Here you had number of modes of vibration was 4, right? 2 stretching and 2 bending vibrations were there. But in the case of water you have only 3 modes of vibration. So for calculating the stretching mode, we have the same equation, that is n minus 1. For both linear and non-linear you have the same equation, n minus 1. So how many atoms are there? 3 atoms are there. So 3 minus 1 is 2. So there are 2 stretching modes of vibration in the case of water. Now how to calculate bending modes of vibration? Bending modes of vibration is calculated using the equation 2n minus 5. Okay, 2n minus 5. Here we had the equation and 2n minus 4, but in the case of a non-linear molecule we have the equation 2n minus 5. So in the case of water, number of atoms will be 3. So 2 into 3 minus 5. 2 into 3 minus 5 is 3 into 2, 6. 6 minus 5, 1. So the number of bending modes of vibration is 1 for a water molecule. Okay, so that is the equations. You don't have to confuse yourself with all these equations. We just have to learn the main one. That is, for a linear molecule it is 3n minus 5, and for a non-linear molecule it is 3n minus 6. And you can learn the stretching modes of vibration equation also. How to calculate stretching modes of vibration? For both case that is n minus 1. Okay, so if you know that total number of modes are 4, and if you know that stretching mode is 2, then automatically you can calculate bending mode, right? You don't have to consider all the equation and all. You simply have to subtract. That's it. These are the equations for calculating the number of modes of vibration for a linear and a non-linear molecule. Hope it is clear now. We have just tabulated all the stuff into one table. That's it. It will be easy for you to study. Okay, so number of modes of vibration for a non-linear and linear molecule. For a non-linear molecule that is 3n minus 6. For a linear molecule it is 3n minus 5. For stretching, number of frequency can be calculated using the equation n minus 1 in the case of linear as well as non-linear. Now bending modes of vibration for non-linear is 2n minus 5, and for linear it is 2n minus 4. Now example is water molecule, example is carbon dioxide. Also draw the structures in the side, because otherwise when you are learning, that time you will get confused. Both are having 3 atoms, then how it became linear and how it became non-linear. Fine. So this is number of modes of vibration. Generally in all competitive exams, one question will be there from this section. How to calculate number of modes of vibration for a linear molecule or a non-linear molecule. Okay, always that will be there in all the exams related with chemistry. So fine. So do learn these equations properly. What happens, we'll get confused, and for linear molecule you'll write the equation 3n minus 6, and for non-linear you'll write at 3n minus 5. Okay, that's all about modes of vibration. Next we have to learn about the region of IR spectra. That is, we have two regions in vibrational spectra. One is skeletal region and the other one is functional group region. So we have to learn about these two regions, and finally the applications. That's it. Okay, so let's learn that. So IR region, generally IR region ranges from 700 to 4000 centimeter inverse. Okay, so we know VIBGYOR, right? That is a code for remembering these values. VIBGYOR. So here violet, indigo, blue, green, yellow, orange, red, right? So violet represent UV region, okay, and red represent IR region. Alright, so remember like this: violet represent UV region, UV ultraviolet, R represent infrared, red region. So UV always ranges from 200 to 600 nanometers. Okay, UV ranges from 200 to 600 nanometers, and IR value starts from 700 to 1400, 7000 to 4000 centimeter inverse. Units are different. Here we are calculating nanometer, that is wavelength. Here we are calculating frequency, that is centimeter inverse. Okay, so 200 to 600 is our UV region, 700 to 4000 is our IR region. So you can remember like that if you know this code VIBGYOR, that will be easy. Okay, now nothing related with the syllabus, I was just telling to remember it. I used to remember like this. Our IR region ranges from 700 to 4000 centimeter inverse. In that we have divided IR region into two. First region ranges from 700 to 1500 centimeter inverse. Okay, and that is called our skeletal region. It is also known as fingerprint region. Okay. Now, our first region, that is from 700 to 1500, that is called skeletal region, or otherwise known as fingerprint region. Now, the second region starts from 1500 to 4000 centimeter inverse, and that is called our functional group region. Okay, that is called our functional group region. So generally we have two types of region in IR. First one is our skeletal region or fingerprint region, and second one is our functional group region. So as the name indicates, if we have a molecule, say for example H2O, water. Okay, if we have a molecule water and you are going to take the IR spectra of water. So water is a particular molecule, right? So for water we'll have a particular fingerprint frequency. Okay, see, I am Sushmita, I'll have a particular fingerprint, and the person who is watching my video will have a separate fingerprint. So for all people or for every molecule, it will have a separate fingerprint, right? For water, it will give spectra and fingerprint region. For ammonia, it will give a different value in this fingerprint region. For carbon monoxide, for carbon dioxide, it will give a different value in the fingerprint region. So for all molecules will have different fingerprint frequencies. Okay, so that values will be getting in this skeletal region or fingerprint region. Okay, so example, in the case of water, the fingerprint value is some 890. Okay, let it be 890. I'm just saying for example, that is not the accurate value. So for water, if it is 890, and when you are taking the spectra and we have a peak at 890, you can say that it is water. Why? Because that is the particular peak for water. We don't have any other peak, like no other molecule will give peak in that particular value. Okay, so for ammonia it is 1200. So if we have a peak at 1200, we can say that that is ammonia, because only ammonia will give that particular peak. Okay, that is fingerprint or skeletal region. Now, next is our functional group region. Functional group region in the sense, depending upon the functional groups, we'll have different peaks in that region. Okay, say for example, if I have an OH group, okay, if I have an OH group is present, then mustly I'll have a peak in the range of 3600. This is the functional group region of OH. If we have a peak in the range of 3600, then we can conclude that our molecule must have a OH group. Okay, and say for example, if we have a peak at 1700, then our molecule must contain the functional group CO, carbon monoxide. Okay, so carbonyl group, sorry, not carbon monoxide, carbonyl group. So if carbonyl group is present, you will have a peak at 1700. If OH group is present, you will have a peak at 3600. Okay, so that is our functional group region. Depending upon the functional group, you will have different peaks in that region. Okay, so when you are taking the IR spectra, you won't be knowing the name of a molecule, and you will be asked to take the vibrational spectra and will be asked to identify which is that molecule. In that case, what analyst will do? He will take the IR spectra of the molecule and he will analyze each and every peaks. Okay, so depending upon the peak, he will come to a conclusion that this molecule is this because it have these many functional groups are present, peak in the fingerprint region also. So finally we can conclude that this is that particular molecule. Okay, so that is the purpose of this fingerprint region and functional group region. Functional group region help us to identify which all functional groups are present in our molecule, and this skeletal region or fingerprint region help us to identify which is that particular sample or which is that particular material that is given to us. Okay, generally we have a reference values of different molecules, and we'll be comparing with that library values, and finally we'll be coming to a conclusion. All right, so IR region is generally divided into two. First is skeletal or fingerprint region, and second one is functional group region. What is skeletal or fingerprint region? That is a fingerprint of a molecule, and you will have a particular value for a particular molecule. No other molecule will give a peak at that particular value. All right. Now, second is functional group region. Functional group region in this functional group region means the region which shows the peak of the corresponding functional group present in that molecule. In that molecule, which are functional groups are present, that values will be highlighted in functional group region. Okay, and the range is 1500 to 4000. This is actually 700 to 1400, but generally we say 700 to 1500 and 1500 to 4000. Okay, so that is all about our IR spectroscopy. So what all things we have learned in IR spectroscopy? First is principle, must you have to learn the principle. Second is simple harmonic oscillator and unharmonic oscillator, energy and vibrational frequency equations. Two diagrams we have learned. Finally, the selection rule for simple harmonic oscillator and unharmonic oscillator, that topic was done. After that, we have learned modes of vibration, how to calculate for a linear as well as for a non-linear molecule. Okay, stretching modes and bending modes also we have seen. After that, you have to learn this IR region. IR region is divided into two. First is fingerprint or skeletal region. Second one is functional group region, and the values you have to learn. All right. Now, finally, we have to learn about the applications of IR spectroscopy. What are the applications of IR spectroscopy? So, what are the applications of IR spectroscopy? First one is determination of its purity. Okay, we can determine the purity of a sample. How to determine purity of a sample? If we have any impurities present in that, that will also give a peak in IR region, right? So you can identify that any impurities are present in the sample. First is to determine the purity of a sample. Okay. Second one is to determine the structure of a molecule. You can identify the structure of a molecule. How many functional groups are present in that, which is the structure of that molecule. So structure identification is yet another application. Okay, structure of a molecule. Now, you can distinguish between intermolecular and intramolecular hydrogen bonding. Just learn like that. You don't have to go much deeply into that. Okay. So you can distinguish between intermolecular and intramolecular hydrogen bonding. So hydrogen bonding is present, then you will have a stretching frequency for OH. In the case of intermolecular hydrogen bonding, values will be different. In case of intra, it will be different. So you can identify either inter is present or intramolecular is present. Next one is identification of different functional groups present in a molecule, right? We can identify different functional groups present in a molecule. Functional group identification. That is another application of IR spectroscopy. Next, identification of force constant. You can calculate force constant using our equation. 1 by 2 pi into root of k by mu, right? Initially we have learned an equation. If you know the stretching frequency and you know the mass constants, then you can calculate force constant k. So initially we have learned an equation, right? Mu is equal to 1 by 2 pi into root of k by mu. In that you can calculate k using that equation. So determination of force constant. Any 3 applications minimum you should learn. Okay. So that's all about our infrared spectroscopy. Hope the class was clear. If you have any doubts, please feel free to comment in my comment box. I'll be giving reply for that. Okay. So if you want me to include any other topics in my class, you can also recommend me that in my comment box. I'll be including that topics also. So if you find my class useful, please do share it to your friends and please do subscribe my channel. So we'll come up with a new video next time. Bye bye.